So my name is Beau Brown. I am an InterNACHI inspector in the Salt Lake City, Utah area. I've been doing inspections for a while. I originally started doing inspections in Hawaii. I kind of fell into that on accident. I was a handyman on Hawaii. I met another home inspector who happened to be on the island doing the same thing I was doing. We were both flying helicopters. And being a helicopter pilot is kind of a gig job. You don't really work a full schedule. You work a little bit, and then when the gig dries up, you don't work anymore. We were doing tours, very seasonal on the island. So you need something to kind of keep yourself busy and cover the bills in between when you're actually flying. And so we all kind of picked up a trade, and it just so happened that one of the guys I met was a home inspector, and he taught me how to do it. And then I was kind of getting tired of the helicopter pilot lifestyle. It's really neat, but you don't make a lot of money, and it's hard on your family because you move around a lot. And this seemed like the thing I could do. It meant that I could move back to where I grew up, Salt Lake City area in Utah, start my own business. I've been doing it for 3 years now. I'm just getting to the point where my firm, or my inspection company, we're gonna need another guy to start doing inspections with us. I'm starting to get overwhelmed, which is why I'm doing this out of the truck. I could not make it home from my last inspection of the day with the clients showing up late with enough time to actually be able to do this on time. So we're doing this from my inspection truck off of my inspection laptop using all the tools that I had present. Not as crisp and clean as it could be, but it's going to be good enough. If you have questions as I'm going through this that you'd like to have answered, I do have the question bubble up. I can see what you guys are asking. If it's a good question that's pertinent to what we're talking about, I'll answer it now. If it is something that I feel like is going to take us off into the weeds, I might mention to you, hey, that question that's going to take us off into the weeds, I'll get to it later. And there is a section at the very, very end here where I'm going to want questions, but please feel free to ask questions by typing them into the Q&A bubble. It should be down at the bottom or at the top of your screen. Type them in, I'll read them, I'll answer them. So let's move forward. Demystifying an HVAC system. The first thing that we're going to talk about when we're talking about an HVAC system is the refrigeration cycle. The refrigeration cycle, pull it open for you here, guys, is just the matter of moving heat around from one place to another. That's as simple as it gets. There's about 1 million different ways to do it. The one that is most common in residential heating and cooling is something that uses phase transition to create a colder environment. And a lot of people, they talk about the cold air blowing in the house. A lot of people are going to be talking about the cold like it's an actual thing that you can produce. But if you say this in front of an HVAC technician, they're going to tell you an HVAC system does not make cold. It removes heat. It removes entropy from a space. So let's kind of get our heads around that really quick. So heat, what is heat? Heat is just energy that is locked inside of a substance that is then transitioning that energy from that substance to you. The heat that us as human beings are pretty good at sensing is the stuff that's in air. That's a contact heat. You can also get it through electromagnetic waves. That's radiant heat. Heat is energy. That's what we're talking about. We are removing the amount of given energy that is in a space so that it is now, there's less entropy in there and it's colder and it feels cold, but you're not making cold, you're removing heat. So that's a big one that I hear people say that all the time. Now to a client, if I'm talking to somebody who's buying a house and they're talking that their HVAC system isn't making a lot of cold, I'm not going to take the time to break them down and go, well, technically, it's not making enough cold. It's not doing a good enough job at removing the heat. I know that, but for speaking to a client, just break it down simple for them. Okay, if it's not making enough cold, it's probably because the system that is designed to remove the cold is not doing, or to remove the heat is not doing the job that it's supposed to be doing. So what the system that we're going to cover most in detail today is a vapor compression cycle system. There's big complicated words when we talk about vapor compression cycle, like superheat and stuff like that. I'm here to break it down and make it a little bit simple and skip some of those more technical industry jargony words. You should be familiar with them. You should know them as a home inspector. You can Google it and learn what that stuff is. But today, that's not going to be the focus of this webinar. We're just going to break it down and make it so that you can talk about this system with a level of competence and not lose the person you're talking to, going too far and getting deep into the industry jargon stuff. So I'm not going to be using words like superheat, phase transition, vapor compression cycle, all that stuff. I'm not going to be using it too regularly. I'm going to try and keep it really simple and easy. So the first thing I want to talk about, now that we've gotten into the fact that we're just moving heat from one location to another, is how a refrigerant system does it. And it uses phase transition in a chemical that is called refrigerant. So the refrigerant that is pumped through the system, it's supposed to boil and change from a liquid to a vapor. Now, one of the neat, unique things that happens when a phase transition happens, that's changing from a liquid to a vapor, from a liquid to a solid. One of the things that happens there is that transition, that change, it requires energy to make it happen. And so if you can force it to occur, it will either absorb or release energy as you are forcing it to go in one direction or the other. Or you could add or remove energy from it, and it would also occur as a side effect of adding or removing that energy. So the refrigerant is a liquid that boils at a very low temperature. That's what most refrigerants are. For example, I think 110A boils at like 26 degrees, negative 26 degrees. And that's really cold. Like it could be freezing outside and you could spill some 110A on the ground and it would boil and evaporate, because to 110A, our normal living temperatures are unreasonably hot. It boils and turns into a vapor incredibly quick in those temperatures. Water does not make a good refrigerant for humans. It does for other situations and other cases. It's not a great refrigerant for humans because water, its boiling temperature is high enough that if you were to heat it up so that it would boil and remove some energy as it changes from a liquid to a vapor, those temperatures aren't doable for humans. We don't want it to be 100 degrees. That's not cool to us. So you need a different chemical that boils at those lower temperatures. And the refrigerants that we have designed are those different chemicals. Originally, R22 was great. It boils at like negative 60. It's an incredible material, but it's bad for the environment. So they decided back in the 1980s, there's a big convention they put together. I think it's the Montreal Convention is what it was. Anyways, they decided that they were going to outlaw R22 refrigerant. And so they were starting to look for replacements for it. They wanted something that didn't have as much chlorine in it. The chlorine is what reacts with the atmosphere and causes all sorts of problems. And it's carried up there because when it evaporates, it becomes lighter, goes up high into our atmosphere, it reacts, and you lose the ozone layer. And so that was one of the big problems that they were having with R22, is they knew that it was going to cause loss in the ozone layer. So what they did is they basically made a structured plan that said that they would start phasing it out over the years. And 2010 was when they said, no more. You can't even make it anymore. You can still have it. It's not against the law to have it. I'm next to the airbase, so you're going to hear the airplane go by. So anyways, you can still have it. It's not against the law to have it in your house. It's not something that if you see a client that has a system that is still running R22, and if you check the data tag, it'll usually tell you if it's running R22, and it's going to be pretty old. You'd be suspicious if it was old. If it's a new system, I wouldn't be too worried about trying to figure out whether or not it's running R22. Because again, in 2010, they said, we're not making it anymore. And so all the R22 that is left over has already been produced. And now what they're doing is they're extracting it from commercial units and other houses and stuff like that when those systems are being decommissioned, and they're selling that to be reused. So it's getting more and more expensive as time gets further and further along. So if you find a system that is running on R22, one of the things that you want to make sure that you tell your client and highlight to them is not that R22 is a piece of crap and that you need to get rid of it and it's dangerous for the environment and all that other stuff. You could talk about that, but honestly, R22 is probably one of the best refrigerants that we've discovered so far. It works really, really well, and it doesn't need a lot of high pressure like some of the new refrigerants that we've got, which means that your condenser is not going to last as long because you need higher pressures. It doesn't need as much high pressure to do the job that it does. And it's also a better lubricant than most of the other refrigerants, which is a problem because you have a compressor and it needs to be lubricated. So R22 was actually really good. It's just bad for the environment. And it's way better thermal efficiency than some of the alternatives we have by like 60% better. It's better at conveying heat at the temperature ranges that we want. You got to remember, when we're talking about conveying heat and cold, these are relative temperatures. Hot to a human being, 100 degrees outside, that's hot to a human being, but relatively speaking, that's not a very high temperature. I can easily heat a piece of metal up to thousands of degrees, and you would call that hot too, but 100 degrees to that piece of metal is a cold temperature because it's at 1,000 degrees. So heat is a relative term, but when we're talking about heat transitions at the temperatures that humans like, R22 is the best. We're currently on 110A. We're moving towards R32 now it is, which is just a base refrigerant. And that stuff actually is really promising. And again, they're going to do the same thing they did with R22 now with the 410A. They're going to start phasing it out. And here in the next 20 years, they're going to stop producing it because it's not a good solution either. It's also harmful to the environment. Not nearly as bad as R22 was, but still enough that when they reconvened for the convention and they were talking about the changes that needed to be done, they decided that that refrigerant isn't good enough anymore either. So the refrigerant, you pump it through the system and you need it to go through phase transition. You want it to boil because when it boils, it absorbs heat. And if you take it from that gas and compress it back down to a liquid, that heat will be forcefully removed from it. It'll be pushed out as you compress it. And you need somewhere for that heat to go. So the way a refrigerant system works is pretty straightforward. We'll pull it up right here for you guys. So this is your basic refrigeration system. Pretty straightforward. I didn't want to include a bunch of the other stuff that can be in here. I'm just trying to explain what the refrigeration cycle looks like. So I picked a very simple diagram. Where we're going to start talking about things are at the compressor. The compressor is the thing inside this system that is responsible for introducing the additional energy it takes to create the pump or the movement of heat in this system. So at a compressor, the suction line side, which would be on your left side of the screen here, it's going to bring in what would be a gas. This is refrigerant that has been boiled. It's going to come into your compressor and it's going to get squeezed down until it is a liquid. You could do this with normal everyday air. Honestly, if you compress the air that's in our environment hard enough, eventually the oxygen, nitrogen, carbon monoxide, carbon dioxide, and other trace gases that are in it will turn to a liquid. It just takes unreasonably high pressures to be able to do that. And there's no mechanical benefit for us. There's other ways to create liquids from gases that are simpler than compressing them. However, when we're talking about a refrigerant, it boils at a very, very low temperature and spends most of its existence as a vapor, and it really doesn't take that much energy to compress it back down to a liquid. That's some of the things that they look for when they're trying to pick the next best refrigerant. How easy is it to compress? What pressure does it produce when it's at a low pressure or a vapor? And what temperatures does it boil at? Those sort of things are considered in a refrigerant. So this system here in front of us could run just about any refrigerant that is currently produced. This system could run on R22 or R44. It doesn't really matter. Sorry, it's 410A is what we're on right now. That's the current best refrigerant. So this stuff here What happens is it gets compressed, and we're a liquid. That liquid is then pumped into a condenser. So the compressor and the condenser, these are the parts that exist outside of the house typically. They're also found on the roof on commercial buildings and in a rooftop unit in RTU. But those two parts are almost always with each other. Sometimes, like when we're talking about commercial units, even the evaporator is inside the same unit. But most of you guys are going to be doing residential. We're going to kind of stick to residential. Your compressor and condenser are two components that live together in that nice little box on the outside of your house. And their job is to squeeze the gas until it turns into a very hot liquid. And then the condenser evaporates, releases the heat that is produced, not evaporate. We're not going to get to the evaporation stuff yet. So compressor put down, and that liquid is then ran to a metering device. This is something that is absolutely necessary for modern day refrigeration to occur. All of the systems that you will come across in a residential building will have a metering device. There's a bunch of different ways to do this. We're on electric metering devices now, but for a long time, they were a metering device that looks a lot like this, which used a tiny little tube that you could usually see kind of coiled up near the metering device. And that tube would be ran out to the suction line. And the temperature difference at the suction line would control how much liquid is being released to evaporate and turn into a gas. And that's what you're really metering. If you release too much liquid, it will not completely turn into a gas before it gets back to the compressor. If you don't release enough liquid, it will overheat and you won't hit your efficiency ranges and you won't cool the air down as much as you ideally could. So why is it a big deal if we get liquid back at the compressor? And that's because the compressor is designed to take something that is compressible and squeeze it down. Liquids are not compressible. So if your expansion valve is malfunctioning and is releasing too much refrigerant into the system, it will kill your compressor. One of the signs that this is happening is a noisy compressor. You're getting a lot of noise because they're starting to get little micromolecules of liquid refrigerant into the compressor, and it's making a ton of noise. There's other reasons why your compressor could be having an issue, but metering device, one of the best ways to tell if that is the thing that might be going bad, compressor gets noisy. A metering device usually kills a compressor before it's caught. And then you've got to replace the compressor and the metering device. And at that point, you're looking at replacing the whole system. So after the metering device, the liquid is ran through an evaporator coil. And the warm air that is blowing through that evaporator coil is going to be warmer than the negative 20-degree boiling temperature of this refrigerant. Unless the air is below 20 degrees, the refrigerant is going to boil in this evaporator coil. And it'll boil and turn into a gas. And that gas is then pumped to the compressor pump and compressed and sent out the discharge line to the condenser, and the cycle repeats. This is where I want to talk about something that I got wrong. I knew that an HVAC system would, there would be a warm line and there would be a cold line. On the right-hand side of the screen, you can see the liquid line leaving the condenser and go to the metering device. It's warm. Also, the discharge line is warm. The suction line is cold and the expansion line is cold. I got on a roof and I filmed a video and said, hey, look at this system here. These two lines, you should be able to physically touch them, and one would be warmer and one would be colder than the other. And that would be indicative of a potential issue if they were the same temperature, because your system is not running efficiently if they're the same temperature. And I called the warm line that I was touching on the roof the return line, and the cold line that I was touching on the roof the feed line. And I was wrong. The return line on these systems is cold to the touch, not hot to the touch. The line that is feeding the system will be hot to the touch, not cold to the touch. I want to check the Q&A bubble. I haven't had it up for a minute. No questions still. Great. Okay, so to continue going on here, the reason why that's happening is because the liquid itself has been cooled by the condenser, but it hasn't been cooled down enough to where us, remember temperature is relative, us would recognize it as cold. Like when you touch it, that feels cold to you. Temperatures that feel cold to human beings are anything that's generally under 60 degrees. And the refrigerant that comes out of this line that is liquid still is generally going to be over 60 degrees Fahrenheit. So it's going to feel warm to the touch. When it gets to the metering device and it is released by the metering device and allowed to expand, that expansion, as it expands, it's going to boil, and that boiling is going to absorb heat because phase change. When a liquid changes to a vapor, it absorbs heat. So that phase change happens. And this line from the condenser to the metering valve generally goes from the condenser, which is that box outside, all the way inside of the house. They don't usually start expanding the fluid until you're really, really close to your coil so that you lose as little of that heat absorption as possible as it travels from the metering device to the coil. So the metering device in this photo is a long ways away, but generally you're going to find it in the house on the side of the air handler in the basement or in the attic or wherever the heck the air handling unit is. And so there's going to be a line on the outside of the house that you could touch. That's hot, that's your feed line, and cold would be your return line. And remember, it's going to the system as a liquid, so you need less space, which means that your return line is going to be smaller. It's a liquid line, or sorry, your feed line is going to be smaller. It's going to be a liquid line, the line going from the condenser to the metering device, and then it's going to expand, and it'd be a larger line because there's a vapor in there, and you need to still move the same amount of material, but it takes up more room now because it's a vapor, so you use a larger line. All right. So we've covered what the refrigeration cycle looks like. Now we're going to move on to the InterNACHI SOPs, and we're going to talk a little bit about what InterNACHI is expecting you to look at as a home inspector. So your heating and cooling SOPs, I've paraphrased this a little bit. The inspector shall inspect the heating or the cooling system using normal operating controls. If you need to plug into the motherboard to check delta V splits and see what the metering valve is being told to do based off of the temperature readout that it's getting from the little sensor that's out there, you're not expected to do that as a home inspector. You're expected to be able to fire the thing up using the controls that are on the wall. If you can't get it to fire up using those controls, then you can put a limitation in the report saying, hey, it's not functioning like it should. You probably need a technician to come out and take a look at this. You're going to describe the location of the thermostat for the heating and the cooling system, the energy source for the heating and the cooling system. Both of those need to be described in your report, and then the inspector shall report as in need of correction any heating system that did not operate or a cooling system that did not operate, and if the heating system was deemed inaccessible. So, like I said, if you couldn't turn the heating system on, if you couldn't fire it up, you went over to the thermostat and you fiddled with the thing for 20 minutes, still couldn't figure it out, got on Google, tried to find a diagram or a manual on the internet because there's a million different thermostats now, still couldn't figure it out, then you need to put something in your report basically saying, this is the reason why I couldn't figure it out. I tried it, I couldn't get it to fire up, there must be something wrong here. And then that also includes if there's anything stacked in front of it. If you walk into a house, remember, we're not supposed to be moving people's stuff. If you do decide to move people's stuff, you take that liability on yourself. It is not something that you're required to do by the SOP. So if the furnace is blocked and you're not going to inspect it because inspecting it is part of the SOP, then you'd better put a reason why in the report you didn't inspect it. So anything blocking it, thermostat doesn't work. Maybe the power's off to it. Every now and then out here, because I have a lot of heating systems, I know there's places in the United States, like Hawaii, that don't have a heater in the house. Out here, there's times where I show up in the early spring and they've turned the heat off to the house and the temperatures are such that I could test the heater, but the gas is off. So that is something that's got to go in the report. So anything that we are not required to inspect. So we're not required to inspect, measure, evaluate the interior of the flues, chimneys, fire chambers, stuff like that. An underground heating tank, not required to take a look at it. If the pilot light is out, or if the heating system needs to have a big fuse or breaker thrown or anything like that to get it on, you show up to the house and the main breaker is off for it. You're not required to turn that stuff on. If you decide to turn that stuff on, you're going beyond the SOPs. I personally, as an inspector, I would turn a breaker on. I would try to get a self-igniting pilot light to light back up by pushing the switch. I'm comfortable with doing that stuff. I am not required by the SOPs, and if I make a mistake doing that, it's on my head, guys. So you got to be careful here and think about the liability that you're willing to take on personally with your own business or the business that you are working for to do these inspections. You don't need to override electronics or thermostats. You don't need to evaluate the fuel quality, verify thermostat calibrations, calculate air and combustion ventilation or dilution or flue gases or any of that stuff. You really don't have to. I'm going to go through the list of things that are above and beyond the SOPs that I do. I'll even talk about what they are, but this is the definitive list here of things that you don't have to do. Same for, it's pretty much identical for the cooling system as well. Sometimes the computer doesn't want to switch screens. There we go. Okay, so we've talked a little bit about the InterNACHI SOPs. Now what I'm going to do is I'm going to dig into my personal inspection process on how I go through these HVAC systems. And so I like to call my inspection process a flow, is what I describe it as. And basically what we're talking about when I'm mentioning a flow is I want to try and knock these things off as I'm moving through the house rather than backing up to go to areas that I've already been to. So for me, I have it broken down to the interior, the exterior, then the roof, and we're going to kind of dig through what I do as I go through the process. So when I get to a house, and what we're going to do is we're going to look at this, guys, from like the HVAC point of view, right? I'm not going to dig into everything that I do as I go through an inspection flow here. I'm just going to talk about what I'm looking for as far as the HVAC is concerned in each one of these areas as I work my way through the house. So the first thing I do when I get to a house is I turn everything on. I turn on the lights. I turn on any appliances that I'm going to be testing, like dishwashers. I make sure the refrigerator's working. I turn on one of the sinks and make sure I've got hot water. I want all of that stuff functional and going as quickly as possible. The reason for this is because it can absorb an incredible amount of time in your inspection process to find there's no hot water after you've already been doing an inspection for an hour and a half and you've only budgeted yourself 2 hours for it and you're just now figuring out there's no hot water and you still have a bunch of stuff left at the end of your inspection that you haven't done yet. You got to spend 30 minutes trying to figure out why the water heater's not working. So I check to make sure there's hot water. I check to make sure all the lights turn on. And then I fire up the HVAC system. That's part of my very first process when I get into the house. I turn the HVAC system on. In Utah, if the temperature is below 60 degrees Fahrenheit, I don't fire up AC condensers. I won't check the AC. I put a limitation in the report stating that I could potentially harm the AC system because at those temperatures, you could start creating ice in Utah with our humidity and everything else that we have going on. And so here in the state of Utah, I don't fire up refrigerant systems if the temperature is below 60 degrees Fahrenheit. If the temperature is above 80 degrees Fahrenheit, I don't turn on the furnace. You can crack heat exchangers by putting too much warm air through them. They are looking for a reasonably cooler air. This is less likely, less of a potential issue. Really, you could probably fire up the heating system closer to like 100 degrees Fahrenheit and probably not suffer any major problems. But it was a practice that I brought forward within my business that I've seen other inspectors doing, and I like it. I have never had a problem with breaking or damaging a system by following those two rules. If temperature is below 60, I don't turn on the AC. If the temperature is above 80, I don't turn on the heater. That means there's a 20-degree sector there for actually here in Utah, about 5 to 6 months of the year that I can use both of the systems. The rest of the year, it's either too cold or too hot, and I'm only testing one, and I put a limitation in the report. After I turn everything on in the house and make sure that it's working, we move on to the next portion of my flow. I will then walk outside of the house, and I'm going to be doing the exterior. Now, for me, the exterior portion that is important for the HVAC system is I am checking the fuel source, and I'm doing a thermal image scan of the exterior of the house. I keep my thermal imager on me. I do it on every single inspection. It's an unbelievable tool. If you don't got a thermal imager, get one, guys, but we're not doing a thermal imaging inspection course. We're doing an HVAC course. I scan the outside of the house because in the summer, if there's a spot of the house that is leaking a ton of cold air, maybe a window that isn't sealing correctly, or a door that isn't sealing up right, or maybe a spot where the cold air is leaking into the attic. I'll even see cold spots on the roof and stuff like that. So I thermal image the outside of the house. It lets me know what if the thermal system inside of the house is doing its job and if it's leaking badly. And then the next thing I do is I check the fuel source for the HVAC system. This would be the heating portion, right? So here are some requirements on how far away this little gas supplier or your gas gauge. It's the meter. That's why I blinked it for a second. Anyways, your gas meter needs to be away from the things around it. And the regulator vent is really what we're worried about. So there's a regulator on this gas meter. If you see where my mouse is, it's down here. I'm pointing at it right there. Yep, there you go. So that is the thing that we're really worried about, because that is designed to be a safety system that would release flammable gas in an emergency situation, and they want that potential gas to dilute before it gets to a location where it can combust. And so there are requirements on how far away things must be from this meter, because it is the point where you are most likely to get a gas leak under normal operation. There's other locations where you'd be more likely to get a gas leak at joints and stuff like that. But if they've put it together correctly and it's working the way it should normally, the only location where it's designed to leak is at that regulator. And so that's why they're really carrying, it's a distance from the regulator, but the regulator is almost really, really close to that meter. And so that's why they talk about the meter and kind of focus on it. But really, the whole point behind it is the regulator. There are code checkbooks that you guys can get. InterNACHI is in big support of the code checkbook. This is just something that I pulled down off of the internet that didn't have a tag on it that said that I couldn't be, giving it out to the public. So there are other sources to get this from. If you're ever curious and you don't have the code checkbook on you, Google's an amazing thing. Just make sure you check your sources, because there is some false information out there, guys. Okay, so I'll check for gas leaks around that gas meter. I have a gas detector that I use, and I will check around the gas meter. I do a thermal scan on the outside of the house, and then I will check the exhaust system to make sure that it's working the way it should be. In the winter, the exhaust system should be putting out hot exhaust air. If I touch it and it's not warmer than the outside air, that is an indication that it is cooling down too much before it exits. It needs to be a powered system if it is. And for those of you guys that don't know what a powered system is, here's a quick rule of thumb. If it is using PVC pipes, it needs to be forcing the air out, and the air that comes out of it can be whatever temperature. You don't need to worry about it. It's going to force the air out. If it is using the shiny metal pipes, it is probably self-drafting. There are some that power draft and use those metal pipes, but it's going to be a high temperature draft. The temperatures that are coming out are going to be high temperature. That's why they're using the metal pipes. And so if you run your hand in front of the exhaust that's coming out of it, whether you find the exhaust at the roof or you find it on the side of the house, you run your hand across that, and the exhaust that's coming out of it is not warm, then there might be a problem. I would start looking for leaks, because that means that it's cooling down to the same temperature as it is outside, and it's going to cause the liquids that are inside of it to condensate, and it'll create leaks. And so that, for me, is an indication that I need to be looking for leaks somewhere around that system. Maybe where it pokes through in the attic, maybe where there's a chase in the wall. When I thermal image the inside of the house, if I find a chase, I'm going to look closely. I'm going to be looking for that stuff. So that is one of the tricks that I use to determine whether or not those systems are doing. It's not foolproof, but that is why I am doing that. And then for the electrical system, the electrical half, which would be the cooling system, I still want to check the energy source that's associated with it, which means that you're checking that that relay or breaker on the outside, the little switch that you can pull the plug out of, or there'll be a breaker for it that should be located near your HVAC system so that you can turn it off and work on it safely. And I'm always checking to make sure that that's there. I'm checking to make sure that it's the right amperage for the system. The amperage is usually on the data tag. We can dig into that if you guys have questions about it, but there's a ton of good content on InterNACHI about that portion. All right, so we're going to be moving on a little bit further here beyond fuel storage and scan for the exterior. Now, the next location that I go to after I'm done checking the exterior, before I walk back inside of the house, is the roof. I'm going to be checking all of the locations that are associated with the HVAC system while on the roof, so I don't have to get up there. I'll also be checking shingles and gutters and trim flashing and everything else. But today, we're just going to talk about the portions on the roof that I care about for the HVAC system. That would be the vents that stick out, the PVC vents that we were talking about for power vented systems for a high efficiency system. We also have the metal pipes that stick out. Those systems, they just use gravity to ventilate. And you want to make sure they're not rusty. You want to make sure that the penetrations that go through the roof look really, really good. And if you're seeing a lot of rust on them, that's a potential that it's cooling too much and there's too long of a run, or it's not built in there correctly. This is a location where mistakes get made a lot, and people don't notice it for years, but it's really easy to mess up ventilation on these things. My best friend is that gas detector. The one that I use uses combustible gases and tests for combustible gases, specifically is what it tests for. And the neat thing is that if the system is working exactly as it should, it won't burn 100% of the combustible gas that is being produced to burn it. And two, some of the gases that are produced as an off gas, like carbon dioxide, is combustible. And so the system will go off when sensing carbon dioxide. It'll even go off when it senses carbon monoxide. So I check around those vent pipes to make sure that the combustible gases that are supposed to be released and the poisonous gases like the carbon dioxide they're supposed to be released are being released in the location that they were intended to and not somewhere else. If you're seeing rust, there's a good chance that you're getting an exhaust leak. So check those exhaust lines with your gas sensor, not just the gas lines. You'll be surprised how often you find leaks. The next thing I'm going to do is I'm going to walk in the house and I'm going to start my flow on the interior house. I have a whole process for it. I follow an exterior wall. I check everything as I go by. I punch it into the stuff. But eventually, I'm going to come to the closet or the utility room or wherever the heck the air handler for this system is located. And I'm going to be checking on that. I want to see if there's any gas leaks there. I want to check the filter to make sure that the filter isn't really dirty or in bad condition, which is an indication that it hasn't been maintained well, and that we need to take care, that we need to mention that that system probably needs to be serviced. I am going to do a thermal scan on the outside of the system. This one is tricky. If you've never used your thermal imager to look closely at what the HVAC system is doing while it's heating or cooling, start doing it regularly. I wouldn't initially use it as a primary indicator device for finding problems because there's so many weird interactions that happen with that system and your thermal imager. But after a good 10 or 11 times looking at it critically, trying to figure out what is normal, like the seams on a vented system from the 80s, that uses like the sheet metal ducting, the seams on that are going to leak, because back in the 80s, they didn't paint them closed like they do now. And so if you start learning by looking at a new system, and you go, oh, all of these seams are supposed to be tight and I shouldn't have air leaking out of around them, and you go into an 80s house that's got an unfinished basement and you thermal image it and you see all the seams are leaking and there's this cold air coming out, and you start calling it out for thermal efficient, that because it's not efficient enough. One, you're not required to do that in the SOPs. Two, there's no reason to do that. An 80 system functions like that. So you want to just be careful. If you're going to start trying to go beyond the SOPs and looking at stuff, make sure you actually know what you're talking about. But it's okay to learn about and try and figure those sort of things out, at least for me. It's okay to try and figure that stuff out. And I scan all the systems now. I do an entire interior scan, but I specifically pull my thermal imager out to scan the air handler when I get into the basement. And the reason why I'm calling it an air handler is because when we're talking about an HVAC system, there's two different components, the part that makes heat and the part that makes cold. The parts that actually cause the temperature exchange to happen generally live in the same box with each other. And you can refer to that box as the air handler. Here in Utah, where I'm located, if I call it an air handler, most of the people I'm talking to have no clue what I'm talking about. I have to call it a furnace. And then they go, oh, I know exactly what that thing is. So that's one of the reasons why I try to stay away from some of the industry jargon, because even by locality, in Hawaii, if you call it an air handler, they know what you're talking about. But in Utah, if you call it an air handler, you get questioning looks. And so I call it a furnace, even though its job is to circulate the air, and the furnace just so happens to have an AC coil on it. And that cools the air too, and most people associate that to be one working unit. So remember, it's two different systems. If you're testing it if I'm testing it at a time of year where I can test both of those systems separately, then I do. But generally, there's a good half of the year where I'm only testing one or the other system, not both of them. So I'll go through, I check the dates and the condition, I check for leaks, I check the filters, and then I do a thermal imaging scan on the entire thing. And some of the common mistakes that I find here in the state of Utah and that I'm used to seeing all the time would be stuff like missing drip legs or dirt legs. That's as the gas comes into the system, you need to have a change in direction, and gravity needs to cause the dirt and dust particles that are in that gas line to fall out into the dirt trap or the dust trap or the drip leg or whatever you want to call it. The dust falls down in there, and it's to prevent it from getting in your regulator. And it's because the regulator in most systems uses a rubber diaphragm to open and close. And if you get a sharp piece of dust in between that rubber diaphragm, you'll break it or tear it or cause a problem, and you can start getting gas leaking past when it's intended to be off. And so that's why it's important to prevent dust from getting in there. I don't see it almost at all here in the state of Utah. I'm not joking when I say 75% of the systems I inspect don't have a dirt leg on them. Some of the other problems that I find here in Utah are, again, on those exhaust systems. There's a lot of mid-efficiency units here, or even low-efficiency units that are still in use in the state of Utah. They're putting high efficiency in all of the new builds, but they've only been doing that in the state of Utah for probably the last 8 or 9 years. So a majority of the homes are mid-efficiency systems. You find problems around them all the time, especially if they're over 20 years old. The metal that's in there, as the exhaust rises up through it, it will cool down. That's what it's supposed to do as it's rising through there. It does cool down. And as it cools down, the vapors that are in it are going to condense. And as they condense out, they're going to bond with the other chemicals that are gases in there that are condensing as well. And it creates an acidic liquid. But it's carbonic acid is what it generally creates. And it'll erode the inside of that pipe from the inside out. And after 20 years of that, it's not surprising to see that it's rusty. So that's something that we see a lot here in the state of Utah. All right, we're getting close to our Q&A section. I wanted to budget about 15 minutes for it. Let's see. Do you have a preferred app, web source for dispersing data tag info? Yes, I do. I like to use, but doesn't provide efficiency info, which you like to include. So I use what I use to to figure out what the data tag is just the old school buildingintelligencecenter.org. Those are the ones that I use. They generally have the information that I need to be able to decode the serial number on the tag and tell me how old it is. As far as efficiency goes, you are opening a can of worms by talking about efficiency. So a house that has a 5-ton unit, they may have installed the 5-ton unit on there because the HOA said that it needed to be a 5-ton unit because they had certain efficiency standards that they needed to meet. But that might be completely overkill for a 1,200 square foot house. A 5-ton unit is way too much. Does it mean that they're going to run into problems and issues with it? They could potentially, but really, the reason why I would even maybe highlight there's the size of the unit on the side of the house, and I don't talk a lot about it to my clients. I understand it, of course, but is for the reason like, okay, so on the side of the house here, this is a 1,200 square foot home. You have a 5-ton unit, and I usually figure out the tonnage. If you want me to get into how to figure out the tonnage, there's an easy trick for that. Let me finish what I'm talking about here, and I'll just probably talk about it. But on those units, when I'm talking about the size, if I'm talking to a client, it's to let them know, hey, 5 tons might be a little too much for this house. When it finally gives out, you'd probably be okay with only buying a 3.5-ton unit. You don't need 5 tons for 1,200 square feet. And that's the kind of conversation that I might have with a client. Would I be looking at a house to go, okay, the house is 5,000 square feet and it's only got a 2-ton unit on it? I don't know if it's going to make it. Well, again, it's a can of worms. What does the insulation in that house look like? If it's got R40 insulation in the attic and the walls are like R28 and it's got an insulated basement and the thing is airtight and no air leaks out of it, you bet a 2-ton unit would keep a 5,000 square foot house pretty cold in the summer, even with high temperatures. But they don't build houses like that right now. Some do, but as an inspector, you can't see in the walls and know what kind of insulation is in there. You're not really qualified to be making the call on whether or not that HVAC system is large enough or small enough. So I don't dig into the weeds with that one too regularly. It's just too easy to get caught by your tail and talk about something that, one, you don't really have the authority to be talking about, and two, remember, you're supposed to be a source of information. If you don't know the whole picture, maybe you shouldn't dig into that topic. Stick to the SOPs until you're comfortable with what you know enough to go above and beyond. I do leak audits and energy audits on houses, but I have a background for that sort of thing. So I'm real comfortable talking about that, but that is above and beyond a lot of the SOPs to do that one service, to do an energy audit. That's well beyond most of the SOPs. So we're getting into questions here, guys. All right, so I'm just going to bump this forward into the question section, and we will get into the questions. I've also got a couple of neat photos in here that I thought were really cool that I found last night, decided to include them. So hopefully you guys ask a question and I can pull one of those photos up because that stuff is fun to talk about for me. But I'm going to pull the question bubble back up and we're going to move on to the next question here. Looking to provide SEER, HUV, etc. That is on the sticker that quickly fall off of the unit. Oh, so you're talking about like that energy efficiency sticker, the yellow one that they put on there that tells you like the SEER and stuff like that. Okay, so you can a lot of times you can get on the internet and put in the model number and then look up if the model number is still there, because a lot of times if that sticker is gone, sometimes a sticker that has the model and serial number on it. You can dig as deeply into the going to like the manufacturer's production website, You can call technicians too. I've got a couple of technicians. If you are a home inspector and you do not have an HVAC technician that is a friend, as soon as you meet one at an inspection, get his card, ask him to go out to the bar with you, make friends with him. Because let me tell you what, I can't even tell you how many times that I've come across something where a client was asking me a question that I didn't 100% know the answer on. And I was like, you know what I can do? I can call this guy. He'll give me answers. I call him. I talk to him. I get the answers. Sometimes I even hand the phone over to the client and they get the answers from him. It's good for me. Makes me look like I'm a source of really good information. It's good for the client because they're getting true, detailed, in-depth information that might be beyond what I'm supposed to be giving out anyways. And it's good for the HVAC technician because that client now has a relationship with him and is more willing to use him if their system is broken. And so a lot of the HVAC techs that I use for that, they're more than happy to pick up the phone. And I've got one guy that if I can't get the SEER rating off the side of it, and I'm trying to figure that all out, and I'm trying to dig through serial numbers or model numbers or try to figure that thing out because it can be a headache if you don't already have the information printed on the side. I call him and I ask him, I say, hey, so here's my question. Here's the model number on this unit. And he's got a professional app that he pays like a few $100s a year for. And it's got all sorts of neat information in it. I just can't justify buying that myself. I don't use it often enough for that. But that is one of the things I would do. So do we have other questions for later? Oh, maybe I marked something as on heat pumps. How much can you determine how the system is running in either system? Only about to run. So a heat pump. So a heat pump, you can run those any temperature you want. The stuff, some of the stuff that happens that you worry about with running an AC system when it's too cold. AC systems are optimized to create as much cold as feasibly possible from the refrigerant that's being pumped through them. Heat pumps, they know they're going to be running them both ways and that you're going to run into some extreme temperatures, and so they have some extra protections in there. Like one of the things that they put inside of heat pumps that you have to have is a bidirectional filter. Which helps with taking care of like running a heat pump at the wrong temperatures and potentially creating a situation where you get liquid. And that's the biggest problem really with a heat pump that you'd be scared of with whether or not it's the right temperature to be running it is getting liquid refrigerant back to the condenser because your temperatures are off in one direction or the other as you're running the system to heat or cool. How much can you know about heating when I can only run cold? So like I said, heat pump, you can turn on the heat or the cold, but the heat pump, if it's too cold to run it, a lot of them will have a safety feature as well that says, actually, the temperature outside is cold enough that you should just open a window. So I hope I answered that one correctly. Let's see, I answered this one. Anonymous viewer, how do you develop those relationships with technicians? So really, I am constantly in an effort to try and find 3 really important guys that I refer work to all the time. It would be an HVAC guy, an electrician guy, and a handyman guy. And I'll start referring work to those guys as regularly as possible. One of the things that I'll do is if I come across an issue and somebody's saying, hey, this is a thing that we're not okay with, and I say, well, that's a handyman problem, or that's an HVAC problem, an electrician problem, I have somebody that I can give that information to and have them talk you through that. They're familiar with my reports. They've seen my reports before. A lot of these guys, I introduce them to my reports. The way I build those relationships is by talking to strangers. So there's been times where I've done inspections on houses in new developments, and there's an HVAC company across the street installing an HVAC system in a brand new house. And I walked over to him as he's climbing out of his van and said, hey man, are you working on this house? He said, yes. And I said, I need an HVAC guy that I can talk to. Do you mind talking to me for a few minutes? I asked him a couple of questions. It was back when I was just starting out here by myself, and I felt like I needed somebody that I could refer to that wasn't living in Hawaii, thousands of miles away. And I basically explained that. I'm a home inspector. I want to know as much as I possibly can, and I'm going to have questions that are like industry specific because I'm in this weird notch where I'm more educated than the layman, but not as educated as you. And I want to be able to fall back on your additional education in the future. I'll offer you a trade if you're willing to play game with me. One, I want to be your friend. I want to build a relationship here. And if you make that clear with somebody, it's amazing how willing they are to work with you. If you just tell somebody, I want to be your friend. I want to work back and forth to do something together. And then the other thing I tell them is exactly what I just said. If there's a question and I have it, I would like you to pick up the phone quick, because generally when I call you, it's going to be a question. I'm going to have a client right there. But here's the neat thing. If it's such a big question that I'm calling you, it's probably because it's a big enough problem that they're going to take action on it. And now you have a relationship with that client, and they're more likely to use you when they need the repair, which means I'm helping pass business along to you. And it'll build your business like crazy. That's one of there's a lot of guys out there that go and roll real estate branches to talk to them about that sort of stuff, and introduce themselves, and they bring candy and stuff into real estate branches to meet realtors. There's a lot of guys that they go to like marketing events, like golf events and stuff like that, and that stuff works. I've done a lot of that. But it's insane how much work I've gotten from a couple of good electricians that I talk to regularly, a couple of HVAC guys that I talk to regularly, a couple of plumbers I talk to regularly, and a couple of handymen that I talk to regularly. I take them out to the bar, I buy them drinks, I treat them like a realtor who's been referring me a lot. And then when they run into clients or customers that are selling their houses, they will tell them, hey, when it comes time, I got an inspector. They usually run into these guys because they're helping them do a repair on their house before they sell it, because their realtor is telling them that they need to do that. And so I get those referrals too. So it's a really good system. I couldn't recommend it more, guys. Make sure that you meet yourself an HVAC technician. Just go find one in the wild. Those guys are pretty cool. Same thing with plumbers, electricians, and handymen. Framers, not so much. Drywall, not so much. Those are the guys that you really need. And I wouldn't even say that a plumber is super necessary, because at least in my area, they're super easy to come across. It's not hard to find a plumber that isn't busy in my area. Okay, guys. So we're getting close to the end here. If you've got any more questions, let's go for it. If I don't see another question pop up here in a minute, I'm actually going to pull up this diagram here. So if you are the type that is constantly looking to learn and improve your trade about what you're doing here as a home inspector, I cannot recommend enough going to the engineeringmindset.com website and looking at their information on heat pumps, looking at their information on just about anything that has to do with a residential house. He has beautifully designed illustrations. He has long, in-depth YouTube videos that are actually kind of entertaining to watch, that'll break all of this stuff down. It's a great place to go. I would also highly recommend InterNACHI's website. If you go to their website, there's a search function in there, and you can search for images that are like this. And then not only that, associated with those images is generally an entire article on the topic that is specifically centered around an inspector's point of view or take on it. And you've got this system here. So we talked about the general refrigerant cycle. This is a heat pump, which this is the direction we're going, ladies and gentlemen. We are going to be doing heat pumps for everything here in the near future. And these systems, it would behoove you as an inspector who plans on doing this for any amount of time. These are the systems you want to get familiar with. The part that's very different from a regular HVAC system and a heat pump system is this reversing valve you see here in the middle, and then the non-return valves, and the fact that there are two different expansion valves, and the refrigerant is always flowing through the expansion valves. It just depends on which direction. So they're unique systems. They're a little bit different, but they work on the same principles. You're just boiling a refrigerant. It's just a matter of where you're boiling it versus where you're releasing the heat out of it changes. So that's about it, guys. We're coming up on the end of this presentation. Thanks everybody for sticking around. I appreciate you guys coming out with the questions. Y'all have a good night. And one more time, thanks for sticking around with me through the technical difficulties.